So now that we've trimmed our sequences, assembled them, and validated them with BLASTX, or annotated them with BLASTX, now it's time to infer their evolutionary relationships with little molecular phylogenetic analysis. The software that we're going to use is called MEGA. It provides us with the tools necessary to take our translations of our contigs and infer phylogenetic relationships between the species from which those cytochrome oxidase fragments were extracted. Let us first open up MEGA. Well, let's first access our sequences. So if you've already translated all of your sequences, go ahead and use those. But of course, if you didn't get an opportunity to do that, then you can use my sequences. The last link in this sequence dataset section contains a multi-FASTA file of all of my amino acid sequences, and here they are. So we just want to have those available for our analysis. First, what we need to do is create a multiple sequence alignment in MEGA. So let's open up MEGA first. My MEGA icon is on my desktop. Let's double click it. When working with MEGA, MEGA will open up a number of windows in addition to what I call the main MEGA window. So we'll have a window for our multiple sequence alignment, and we'll have a different window for our phylogenetic tree. What we're going to have to do is take these sequences, copy and paste them into MEGA, and then create a multiple sequence alignment. First, if you go to the MEGA window, click on the Align button, and then click Edit Build Alignment, and then select Create New Alignment, and then select Protein. Here is our Alignment Explorer window. So now go to the browser. If you opened up my sequences, hit Control-A and then Control-C to copy all of the sequences. Navigate back to the Alignment Explorer and then hit Control-V, and now all of the sequences are pasted into the Alignment Explorer. To the far left, you'll see the FASTA header information or annotations, and then to the far right, you'll see the amino acid sequences. Now, this is not an alignment. This is just the raw sequence information listed in MEGA. In order to create a multiple sequence alignment, well, there are two options. There's Cluster W, and there's also one called Muscle. I prefer to use Muscle. So if you click on Muscle and then select Align Protein, you're going to get this message: nothing selected for alignment, select all. With this feature, or with MEGA, you can create a multiple sequence alignment with some subset of your entire data set or everything. If you want to create an alignment with everything, go ahead and select all, and that's what we want to do. So click OK, and then accept the default parameters. Click Compute, and now we have a multiple sequence alignment. What I want to do is I want to actually look at the alignment in a little more detail. So let's go ahead and squeeze this window in, and we'll squeeze this window, and we'll expand this a little bit. So notice there are columns that are complete with identical matches or identical characters, and they're highlighted with asterisks. And there are some columns with some substitutions or amino acid changes. Now, the gaps on the ends of the sequences in our analysis have no meaning, and if these sequences were complete, these gaps would represent an insertion or a deletion event. So what is this multiple sequence alignment telling us? It's revealing to us that there are portions within this protein family of cytochrome C oxidases that are more forgiving to change or more forgiving to substitutions. And there are other regions that are less forgiving to change. So it is this collection of similarities and differences that will allow us to group similar sequences together and separate more distantly related sequences from each other, and then diagram these close and distant relationships in the phylogenetic tree. Now we won't do this by hand. We're going to allow the software to do it for us. And this multiple sequence alignment will serve as the input for our phylogenetic analysis. Let's go ahead and create a tree. So before we do that, let's go ahead and save this alignment somewhat as a backup. So if you go to Data, then click on Save Session, and then we'll choose a name. I'll choose Bugs underscore COI underscore MSA.MAS. Save. So as you can see, I've already created this file, so I'll go ahead and overwrite this. Most of you won't see this message, so I'll just replace it. Now let's go ahead and create our phylogenetic tree. So if you go to data and then click on phylogenetic analysis, what we just did is we created what's called a .meg file for Mega, and this .meg file is going to allow us to analyze this multiple sequence alignment using one of several different analysis procedures. So if you go to your Mega main window, let me minimize my browser. In the Mega main window, you have a button called phylogeny. If you click on it, it gives you several different types of analysis that you can apply to your data. We're going to use maximum likelihood. So go ahead and click on maximum likelihood. And the reason why we do this is because maximum likelihood is it tends to be more accurate than the other analysis procedures. Like I mentioned earlier, when we clicked on the phylogenetic analysis button, it created this .meg file, or it transformed this multiple sequence alignment to what's called a .meg file, and then uploaded that, and it's this .meg file that we're now going to that Mega is going to use to analyze the data and create a tree. So go ahead and click yes. Now you have this window that opened up. Typically we would accept the default values, but I think when you first install your software, the maximum likelihood parameter for phylogeny test is set to none. We actually want to change that to bootstrap method, and go ahead and insert 100 for 100 replications, and then you can go ahead and select the default parameters, all the other default parameters, and then click compute. Here you'll notice the progress bar. And then once it's finished, you'll then see our phylogenetic tree. So this tree is the most likely tree of all the trees that were explored during that maximum likelihood search. Here's a log of our likelihood score down here. So what's going on in this tree? So first of all, in this phylogenetic tree, the horizontal lines are referred to as branches, and they depict a certain amount of genetic change that has occurred. And these branches actually represent evolutionary lineages that have been changing over time. So the longer the branch in the horizontal direction, the larger the amount of change that has occurred. So if you look at the scale bar down here, this 0.05 refers to the number of substitutions per site, and it's actually calculated by the number of substitutions divided by the length of the sequence. The vertical bars have no meaning. They just serve to give us an ability to separate the information from the horizontal lines, so that we can better see the text and better understand, or better get an idea of what's going on in our tree. A tree is depicted with only bifurcating nodes, and not this trifurcation or multifurcation. What's happening here? This can be interpreted to mean that of all the trees that were analyzed, this tree with this trifurcating node was the most likely tree, or had the tree with the best likelihood score. So it looks like there's one node and it splits into three. But however, we can modify this display. We can actually look at the topology alone, or the shape of the tree alone, without looking at branch lengths. So if you click on this button here, it actually now changes the tree, so now that we only see the topology of the tree. So when we look at the topology without the branch lengths, we can see that this American house and this gold weaver are more closely related to each other than the spider is to these other two sequences. So what are these values that are at the nodes? So these numbers represent a measure of support for that node, and these values in Mega range from 0 to 100. And these were computed by the statistical approach called bootstrapping. So in short, just understand that the higher the value of this bootstrap, the more support there is in the data that the sequences to the right of the node cluster together as compared to other sequences. So what that means is that at this node here, this node has a score of 98, almost perfect. What that means is that out of those 100 trees that were generated from the bootstrap replication process, these three sequences cluster together 98% of the time. So this low bootstrap value can be interpreted to mean that we really cannot trust that these two sequences are more closely related to each other than to say anything else in this tree. However, we can be really confident that these three sequences are more closely related to each other than they are to any other sequences. So let's go back to the branch style, or looking at the branch lengths. Now, the default setting in Mega is to root the tree at what's called the midpoint. So if you click on View, it's currently rooted at the midpoint. And what that means is that at this point here, there is, if you would add up the distances of all these branches on one side of the node and add up the branch lengths on the other side of the node, they would be equal. However, oftentimes people would like to root the tree to some ancestral sequence. And so if you wanted to do that, you would have to beforehand add some outgroup sequence, or some sequence that you know to be more distantly related to the data set, to serve as some reference point or some root. Or otherwise, you can examine the tree and maybe identify a sequence that you think may serve as the best root for this tree. Let's say, for example, you wanted to set this sequence as the root for the tree. You can click on this button here, place root on branch, and now when we go to this branch and click on it, oops, it didn't work. There we go. It set the root of the tree to this sequence, and so now it appears as though all of the other sequences originated from this CADE sequence and then split at this node into these two main branches. Another thing that you might want to do with Mega is to change the text. Let's say that you wanted to delete the information at the beginning of the header line. Well, if you were to double click on the text, you can then go in and delete it, and you can modify the text to anything that you would like. So that's my lecture on phylogenetic trees.